Hello, my dear students. Exams are near, no? I can feel the tension building up, but don't you worry at all. Today, we are going to make this chapter coordination compounds super simple for you. Trust me, by the end of this, you will feel like a master of this topic.
Have you ever stopped to think, why is our blood red? Or how come a ruby is that beautiful deep red, but an emerald is green? It's not magic, my dear children. It's chemistry. So chalo bachcho, let's become chemistry detective today and solve this colorful mystery. The answer to all these questions, it lies in one very important topic: coordination compounds.
It's actually very easy. In the next few minutes, we'll cover the chemistry mystery, then Werner's big idea, meet the compound family, learn how to name them simply, uncover the secret of their color, and finally, see why these compounds matter so much. Okay, are you ready? Let's dive right into this.
All right, so our story starts with a great scientist, Alfred Werner. People often call him the father of coordination chemistry, and for good reason. He was the very first person to really properly understand these special compounds.
So Werner came up with this really simple idea of two types of valency, or you can just think of them as bonds. The first one is the primary valency. This one is ionizable, meaning it can break apart in water. Think of it like a weak link. It corresponds to the oxidation number and is usually satisfied by negative ions. But then there's the secondary valency. Now this one is strong. It's non-ionizable, so it doesn't break in water. This corresponds to what we call the coordination number, and it can be satisfied by neutral molecules or ions.
Okay, now let's get to know the key players in our compound family. To make it super easy to remember, just imagine it's like a big house, a palace, with a king and all his ministers.
So you see those square brackets? The whole thing inside the square brackets is what we call the coordination entity. Just think of it as the main royal palace. Everything inside is one single unit, okay? It doesn't break apart. And right in the middle of this palace, we have the king. This is our central atom or ion. In our example, that would be the cobalt ion. He's the main guy. All the action happens around him.
And what about all those groups attached to the king? Well, we call them ligands. They're like the king's loyal ministers, always surrounding him. So you have the king, the central atom, and his ministers, the ligands, all inside the palace, the coordination entity. Simple, right?
Now listen very carefully. This is a very important question for your exam. The difference between a double salt and a complex. It's so simple, Baba. A double salt, like Morse salt, loses its identity when you put it in water. It just breaks up completely into simple ions. But a complex combination, oh, that's different. It's strong. It retains its identity in water. The part inside the square brackets does not break apart. That is the key difference.
All right, naming them. I know this part can look a little bit scary, but trust me, it's just a few simple steps. Let's see how it's done.
You just have to follow these 4 simple steps, and you'll be able to name any compound they throw at you. First, you name the cation. That's the positive part. First. Simple. Second, you name the ligands, but you have to do it alphabetically. And remember, some have special names, like amine for NH3 and aqua for H2O. Third, you name the central metal atom. Here's a little trick. If the whole complex is an anion, meaning that's negative, you add at to the end of the metal's name. And finally, step 4, you write the oxidation state of the metal as a Roman numeral in brackets. That's it.
Okay, time for a quick practice question. This is a very common type of question you'll see in your exam. So, what is the IUPAC name for this compound? Go on, apply the rules we just learned. Don't worry, take your time.
Did you get it? The answer is diamine chloronitrito N platinum 2. Excellent. See? We named the amine first because A comes first alphabetically, and there are 2, so diamine. Then chlorido for C, then nitrito. Then the metal, platinum, and finally its oxidation state, which is 2. Simple, no?
And now, let's solve our big mystery from the beginning. Why are these compounds so colorful? The answer is something called crystal field theory. It sounds complicated, but I promise the idea is actually very simple.
So what happens is this. When our ministers, the ligands, come close to the king, the central metal, they cause the king's d orbitals, his energy levels, to split into 2 different sets. You get a lower energy level and a higher energy level. This splitting is the entire secret.
Now, because there's this gap between the energy levels, an electron from the lower level can get excited and jump up to the higher level. But to make that jump, it needs to get a boost of energy. And where does it get that energy? It absorbs it from sunlight. This little jump is what we call a DD transition.
Okay, and this is the most crucial point. The color that you see is the light that has left over after some of it has been absorbed for that electron to jump. So, if the compound absorbs, say, yellow light from the sun, you won't see yellow. You will see its complementary color, which is violet. And that is the secret of the gems.
So why should we study this chapter so hard? Is it just for the exam? No! It's because these compounds are literally everywhere, and they're doing the most amazing things.
I mean, just look at this. Hemoglobin, the iron complex in our blood that carries oxygen, is one of them. Chlorophyll, the magnesium complex that helps plants make food, is another. Even vitamin B12, a cobalt complex that's essential for our body. And it doesn't stop there. Cisplatin is a platinum complex used to treat cancer, and EDTA helps remove lead poisoning from the body. They are real-world superstars. So you see, chemistry isn't just something in a textbook. It's literally inside you. It's all around you. When you study this, you're learning something truly important and absolutely fascinating. Now you know the secret of color. What other mysteries of the world do you think chemistry can help us unlock? Keep thinking. Go on and ace your exams, my dear students. All the very best.